Let's discuss next topic of dynamic programming. It's optimal binary search tree. Suppose we have three key 1, 2 and 3. In this three key, how many binary search tree possible? In binary search tree, left child is always less than parent, whereas right child is greater than parent. Suppose we'll take 1 as parent, then 2 can be its right child, then 2 right child can be 3. Then 1 right child can be 3, then 3 left child can be 2. Suppose we will take 2 as a parent, 1 can be its left child, 3 can be its right child. Suppose we will take 3 as parent, 3 left child will be 2, 2 left child will be 1. Then 3 as parent, 3 left child can be 1, 1 right child can be 2. So for 3 keys, 5 different binary search tree possible. If I want to search 1, then in first binary search tree, 1 will find in level 1. Now in this binary search tree, we'll find 1 at level 1. 1 is less than 2, so we'll search in left part. Now is this equals to 1? Yes. So we are searching in 2 level. In this binary search tree, first we'll compare 1 with 3. 1 is less than 3, then 1 with 2. 1 is less than 2. Next, is this 1? Yes. So we are searching 3 level to find 1. Next, in this tree, we'll compare 1 with 3. 1 is less than 3. This matches with 1, so we are searching 2 level. So in different binary search tree, searching cost is different according to the tree structure. So how will create the binary search tree that searching cost will be less? For every key, some probability will be given and accordingly we need to search. So how will create the optimal binary search tree that total searching cost will be less? Suppose we want to search 4 in this binary search tree. So we'll compare 4 with 2. 4 is greater than 2. Next 4 with 3. 4 is greater than 3. So 4 is not present in this binary search tree. So there can be successful search, also unsuccessful search. We are given a sequence k equals to k1, k2 up to kn of n distinct key in sorted order, and we want to build a binary search tree from those key, and for every key some probability is given. Let pi is probability for ki. Some searches may be for the value which are not in k. So there are n plus 1 domain keys like d0, d1, d2 up to dn representing values not in k. So k1, k2 up to kn are values present in k, and d0, d1, d2 up to dn are domain keys which are not present in k. Suppose we have a binary search tree 5, its left child is 1, its right child is 10. These are the key 1, 5 and 10. So we have D0, D1, D2 and D3. D0, any value which is less than 1, that is D0. Then D1, D1 is 2, 3, 4. Suppose we are searching 2 or 3 or 4, that will be D1. Then D2 will be 6, 7, 8, 9. Then D3 will be any value greater than 10. Suppose we want to search 12. 12 is greater than 5. Then 12 is greater than 10. Then we will search here. It's unsuccessful. So D0 represent all value less than K1 and Dn represent all value greater than Kn. And we can say Di represent all values between Ki and Ki plus 1. Like D1 is in between 1 to 5, all value between 1 to 5. For each domain key, we also have probabilities, it's Qi. For key, probabilities Pi, and for domain key, probabilities Qi. So every search is either successful or unsuccessful. We can say sum of I equals to 1 to n Pi plus sum of I equals to 1 to n Qi equals to 1. Pi for successful search, Qi for unsuccessful search. So for a given set of probability, we want to construct a binary search tree whose expected search cost is smallest, and we call it as optimal binary search tree. So our task is to construct a optimal binary search tree whose expected search cost will be smallest. And how many binary trees possible? Suppose we have n keys, then number of distinct binary search tree possible is same as Cattler number. It's 2n/cn divide n plus 1. Suppose n equals to 3, then 6c3 divide 4. So 6 factorial divide 3 factorial multiplication 3 factorial multiplication 4. 6 factorial we can write as 6 multiplication 5 multiplication 4 factorial divide 3 multiplication 4 factorial. So this 4 factorial will be cancelled. Then 3 factorial will cancel with 6. So we have 5 distinct binary search tree possible for 3 keys. Let's see one example. We have two binary search tree for n equals to 5 with following probabilities. These are the probabilities. Now this is our first binary search tree and this is our second binary search tree. What will be expected cost for first binary search tree? So for node K1, K1 is at level 2, or you can write depth 1. So when you are considering depth plus 1 you need to multiply, and probability is 0.15. So 0.15 multiplication 2. Depth is 1, that's why 1 plus 1 with 2 we are multiplying. So contribution will be 0.30. Or you can consider level 2. This is our level 1, this is our level 2, this is level 3. Next K2 is root, it's at level 1. 0.10 multiplication 1, it will be 0.10. Then K3 as level 3 or depth 2. So 0.05 multiplication 3, it will be 0.15. Then K4 is at level 2. 2 multiplication 0.10, it's 0.20. Next K5 is at depth 2. So 2 plus 1, it's 3 multiplication 0.20, it's 0.60. Now all keys are done. Next we'll do for dummy keys. D0 is at depth 2, depth 1, depth 2. So 2 plus 1, it's 3 multiplication 0.05, it's 0.15. Next D1 is at depth 2. So 2 plus 1, it's 3 multiplication 0.10, it's 0.30. Then D2 is at depth 3. 1, 2, 3. 3 plus 1, it's 4 multiplication 0.05, it will be 0.20. D3 is at depth 3, or you can say level 4. 4 multiplication 0.05, it's 0.20. Then D4, so 4 multiplication 0.05, it's 0.20. D5 depth 3, 4 multiplication 0.10, it's 0.40. So after addition we are getting 2.80. So expected search cost for first binary search tree is 2.80. If we'll find for second binary search tree, it's 2.75, and this is the optimal. There are 5 keys. For n equals to 5, how many binary search tree possible? 10c5 divide 6. So 10 factorial divide 5 factorial, 5 factorial multiplication 6, 10 multiplication 9, multiplication 8, multiplication 7, multiplication 6 factorial divide 5 factorial, multiplication 6 factorial. This 6 factorial will be cancelled. 5 factorial you can write as 5 multiplication 4, multiplication 3, multiplication 2. So this 4, 2, that will cancel with 8. 10 divide 5, it's 2. 9 divide 3, it's 3. 2 multiplication 3, it's 6 multiplied 7, it's 42. Now for 5 keys, 42 binary search tree possible. So how we'll know which tree is the optimal binary search tree? So which tree will give less expected search cost? So for that we have a recursive solution. Let Eij as the expected cost of searching an optimal binary search tree containing the keys ki till kj, and ultimately we want to find E1n. Eij equals to qi minus 1 if j equals to I minus 1, else minimum r greater than equals to I less than equals to j, e I r minus 1 plus e r plus 1 j plus w I j. For I less than equals to j, you can do one thing, you just find this part e I r minus 1 e r plus 1 j, and from that whichever is minimum r w I j with that. We need to create 3 table, one for e, another for root ij, that will record the root of the subtree, and another for storing the w. Means every time we don't need to find from the scratch, we can maintain a table for wij and we can use that values. So for the base case, I minus 1 equals to qi minus 1, for 1 less than equals to I less than equals to n plus 1, else wij equals to wij minus 1 plus pj plus qj for j greater than equals to I. So these are the recurrence relation. Based on it, there is an algorithm for finding optimal binary search tree. P, Q, N are given. P and Q are probability and N is the number of keys. Step 1 will create 3 tables. E indexer 1 to n plus 1 0 to n, W indexer 1 to n plus 1 0 to n, and root indexer 1 to n 1 to n. We'll create 3 tables E, W and root. For I 1 to n plus 1, E of I minus 1 equals to Q I minus 1, W I minus 1 equals to Q I minus 1. These two are our base condition. Next for L equals to 1 to n, for I equals to 1 to n minus L plus 1, J equals to I plus L minus 1, Eij equals to infinite, Wij equals to Wij minus 1 plus Pj plus Qj. We'll use this formula for finding W. Next 10 for R, I to J, T equals to E, I R minus 1 plus E R plus 1 J plus W I J. Then if T less than Eij, then Eij will be T. So we are finding minimum value from different R. Now root Ij will be R and will return E and root. From E table we can find the expected search cost. From root we can create the binary search tree. W table is just used to find other table value. And here running time will be theta of nq due to these 3 nested for loop. Let's take the same example. We have 5 keys with probabilities. These pi are probabilities for key and this qi are probabilities for dummy key. We'll create 3 tables E, W and root. In E base, I minus 1 equals to Q I minus 1. So 1 to 0, it's Q0. E2 to 1, it's Q1. Then E3 to 2, it's Q2. E4 to 3, it's Q3. E5 to 4, it's Q4. E6 to 5, it's Q5. Also in W, the base are the Q value. These two lines are for base. So first fill the W table. W11 will be W10 plus P1 plus Q1. So W10 is 0.05 and P1 is 0.15, Q1 is 0.10. Sum will be 0.30. Now check W11 is 0.30. 0.30. So like this, first fill the W table by using this formula. Wij equals to Wij minus 1 plus Pj plus Qj. Next, we will fill both table E and root. How will find E11? R value is greater than equals to I, less than equals to J. So R can be 1. Now E1, then R minus 1. So 1 minus 1, 0, plus E, R plus 1, it's 2, J is 1, plus W11. W11 is 0.30. Now E10 is 0.05. Then E21 is 0.10 plus 0.30 will get 0.45. So E11 will be 0.45. And for R equals to 1, we got this value. So R11 will be 1. As for E11, there will be just one R will be 1. E22, R will be 2. For E33, R will be 3. For E44, R will be 4. For E55, R will be 5. So here you can write 1, 2, 3, 4, 5 as there will be just one R. Suppose we want to find E12. R can be 1 and 2. Now for R equals to 1, E of 1, 0, R minus 1 plus E of R plus 1, 1 plus 1 it will be 2 and J is 2, E of 2, 2 plus W 1, 2. For R equals to 2, E of 1, 1, 2 minus 1 it's 1 plus E of 3, 2 plus W 1, 2. You can just find E part and whichever is minimum you can add Wij with that. Now E of 1, 0 it's 0.05. E of 2, 2 it's 0.40 and W of 1, 2 0.45. Now E of 1, 1 is 0.45. E of 3, 2 is 0.05. W of 1, 2 is 0.45. Here we got 0.45. Here we got 0.50. 0.45 is lower than 0.50. So for R equals to 1, we are getting 0.90. E12 will be 0.90 and R12 will be 1. As for R equals to 1, we got minimum. So like this, you fill both E table and root table. Now after finding root table, we need to construct the optimal binary search tree. Root of 1 to 5 is 2. So 2 will be root. In binary search tree, left child is less than parent, right child is greater than parent. Before 2, just one key. So 1 will be left child of 2. Then after 2, there is 3, 4, 5. Now check root of 3, 5. Root of 3, 5 is 5. So for 3, 4, 5, root will be 5. Now check for 3, 4, what is root? For 3, 4, root is 4. So 4 will be left child of 5. Now 3 will be left child of 4. Next we'll add the dummy key D0, D1, then D2, D3, D4, D5. So this will be our optimal binary search tree for which expected searching cost will be lowest. It's 2.75. For GATE exam point of view, optimal binary search tree is not that important, but still it is in syllabus, so you should know it. With this, I am finishing dynamic programming chapter. In next lecture, I will discuss hashing. And if this lecture is helpful for you, please like, share and subscribe. Thank you.